everyone watching. Welcome to the video of packed bed reactors in chemical reaction engineering. Today we are going to be talking about the uses of packed bed, its elements, its setup, and what are the other forms of packed bed. Our aim for the video is to find out the rate constant for saponification in ethyl acetate and NaOH in packed bed reactors. So as we know that packed bed reactor is used in many chemical industries for the smooth functioning of the process and easy development of the product. Packed bed reactors are a type of flow reactors. The reaction takes place in the bed of solid particles. These particles are in the form of beads or pellets. The reactant flow through the pellets and the reaction takes place. Components of a packed bed reactor. Let's break down the key components of a packed bed reactor. The reactor vessel. This is the shell that holds the packing material and withstands operating conditions like pressure and temperature. Packing material. These are the solid particles, typically catalysts, which can be in the form of beads, rings, or pellets, or structured packing. Fluid inlet and outlets. To introduce reactants and extract products, these are essential. Support grids. Support grids hold the packing material in place while allowing the fluid flow. Last, temperature and pressure controls. These are essential for monitoring and ensuring safe operation. Each component work together to ensure efficient reaction and process control. How does a packed bed reactor work? Here's how a packed bed reactor operates. The fluid flow in that reactants enter the reactor and flow through the packed bed through solid material. And then it follows through the reaction flow. The reactants interact with the catalyst on the surface of the packing material. This is where the desired chemical reaction occurs. Then follows the heat and mass transfer. During the reaction, heat may be generated or absorbed. The packing material facilitates effective heat and mass transfer, ensuring reaction efficiency. Last is the product collection. Whatever product we got through the reaction exit the reactor through the outlet, sometimes requiring separation or purification downstream. One common example is in ammonia synthesis, where hydrogen and nitrogen gases react in the presence of iron-based catalyst in a packed bed. Animated flow of reactants through a packed bed reactor showing the reaction zone and product outlet is the visual aid. How does packed bed reactor compare to other type of reactors like fluidized bed or stirred tank reactors? Packed bed versus fluidized bed. Packed bed reactors are more stable as compared to the fluidized bed reactors, but may have higher pressure drops, whereas fluidized beds are better for reaction needing uniform temperature. Packed bed reactor versus stirred tank reactors. Packed bed are better for continuous operations, while stirred tank are ideal for batch reactions. The choice depends on the process requirements, including reaction type, scale, and economic considerations. Packed bed reactors have several advantages. High efficiency due to large surface area for reactions. It has compact design which saves space. It is flexible to operate under a wide range of pressure and conditions. Now, while having some advantages, it does surely have some challenges as well, which includes pressure drop. The packed bed can cause significant resistance to fluid flow, increasing energy costs. Hotspots. Uneven temperature distribution can occur, potentially damaging the catalyst. Maintaining. Replacing the packing material can be labor intensive and costly. So with this, we conclude with the introduction of packed bed reactor. In summary, packed bed reactors are indispensable in the chemical process industries, offering efficiency, smooth functioning, and versatility for a range of applications. We've covered their components, working, principle, advantages, challenges, disadvantages, as well as their role in the industrial applications.
After having an understanding of basic part of packed bed reaction, we'll move towards the Reaction mechanism of saponification reaction in a packed bed reactor. Let us understand today the saponification reaction of sodium hydroxide with ethyl acetate in a packed bed reactor, which is a classical example of second order homogeneous non-catalytic reaction. H3COO C2H5 plus NaOH gives rise to CH3COO Na plus C2H5OH. The nature of the given reaction is a liquid phase reaction. It is second order because the rate depends on the concentration of both NaOH and CH3COO C2H5. As the objective of the experiment is to determine the rate constant K and to study the kinetics of the saponification reaction in packed bed reactor, let's have a quick look on reaction equation. The rate equation for the saponification reaction is minus Ra equals to K Ca Cb, where Ra is a rate of equation, K is a rate constant, Ca is a concentration of sodium hydroxide, and Cb is a concentration of ethyl acetate. After that, we will understand conversion, which is XA. XA equals to Ca0 minus Ca upon Ca0. For an ideal PFR, there is no mixing in the direction of flow, and complete mixing will occur in the direction perpendicular to the direction of flow. Concentration of reactant varies along the length of the reactor, but not in the radial direction. In the case of packed bed reactor, an additional contact surface is provided for the reaction with packed bed. It is expected that the effect of reaction should be high in case of packed bed reactor as compared to equal volume plug flow reactor. After having a basic understanding of packed bed reactor and saponification reaction, I am going to give you additional insights of this kind of reaction. For this kind of reaction, for model validation, we can use a simulation softwares. Experimental results can be validated using software tools like DWSIM for process simulation and MATLAB for solving the reactor design equations. As we know that optimization is critical in plant operation. In point of view as a chemical engineer, optimization is really important in the process industries. To investigate the effect of inlet temperature and flow rate on conversion, minimize the axial dispersion through better packing design, we use various softwares and modeling equations. With this, we are about to end the part of the theory of packed bed reactor. After this, you will get to know about experimental procedure in detail.
The apparatus used in the packed bed reactor are conical flasks, measuring cylinders, burette, and the chemicals required are 0.1 normal hydrochloric acid, 0.1 normal sodium hydroxide, and phenoxylin as an indicator. Setup of a packed bed reactor. First, we will understand the parts of the packed bed reactor. We have rotameters. There are two rotameters corresponding to the two reactants we are using. The first reactant is the sodium hydroxide and the second reactant is the ethyl acetate. Along with this, we have a gauge pressure adjusting valve which we are using to adjust the pressure inside the reactor. After that, we have two valves. One is over here and other is over here. The bottom valve is of the is for draining the reactor, and the upper valve is for collecting the sample. The feed tanks which are used to store the reactants. These are connected to the rotameters, and as we adjust the flow in the rotameters, they supply the reactant to the reactor. This is an air compressor. During the reaction, the reactants go in the reactor from the bottom. For helping the reactants go against gravity, this air compressor is used. After that, we have the actual reactor in which the reaction takes place. This is a long, narrow, hollow cylindrical tube filled with packing materials known as rashing rings. These rings are the packing material used for helping better contact between the reactants. These rings also help break down the big bubbles happening in the reactor. Let us understand the procedure of a packed bed reactor. First of all, we will switch on the main switch. After switching on the main switch, we will keep our gauge pressure at 1 kgf. After that, we will keep our flow rates at 5 lph each by using the rotameters. Rotameter A corresponds to the reactant A, which is sodium hydroxide, and rotameter B corresponds to the reactant B, which is our ethyl acetate. Are connected to the feed tanks in the back, from which the reactant enters in this tube. This gauge pressure valve is to maintain the pressure inside the reactor. Every minute, we will collect 20 ml of 0.1 normal hydrochloric acid in this measuring cylinder. Collecting the hydrochloric acid, we will transfer it in a conical flask. Now we will add 1 to 2 drops of phenolphthalein in it. After the wait of 12 minutes, we will collect our sample from here. We will open this ball valve and the sample will come from here, and we will collect it in the measuring cylinder. After collecting the sample, we will close the ball valve and let it go back again. We will take this 20 ml sample and add it to a conical flask containing 0.1 normal hydrochloric acid and few drops of phenolphthalein indicator. After adding our sample to this conical flask, we will titrate it. Now we will add the sample collected from the packed bed reactor in the conical flask containing hydrochloric acid and phenolphthalein indicator. Now we will titrate this again 0.1 normal sodium hydroxide from the burette. Now we will fill the burette with 0.1 normal sodium hydroxide. We will titrate the solution again 0.1 normal sodium hydroxide. We will continue this titration till we achieve the color of pink. That will be the end point of our titration. Now we have completed the titration for the flow rate of 5 lph. Now we will start the closing procedure. First we will make sure that the rotameters are back at its initial position, that is at 0. Along with it, we will make the gauge pressure indicator at 0. After that, we will drain the reactor using the ball valve given below. After the reactor is drained, we will again close the ball valve. Now we will switch off the main switch. Once this is drained, we will again set our flow rate for 7.5 lph and we will again repeat the procedure. For this, we will wait for 6 minutes. Demonstrated the procedure for the flow rate of 5 lph. After that, we will repeat the procedure for the flow rates of 7.5, 10, 12.5 and 15. In conducting the procedure, we need to take the precautions that while conducting the procedure, sometimes the flow rates of the rotameter drop or rise. We need to keep a watch that they do not rise or fall, and if they do so, we have to adjust them back to their original flow rate. Also, for the pressure gauge, the pressure gauge mostly increases. We have to make sure that we keep it back on 1 kgf.
Part of video, we have seen the theory of saponification reaction in packed bed reactor, detailed explanation of experimental procedure of packed bed reactor. Now let's see and understand the calculation part of this experiment. The aim of the experiment is to study the kinetics of reaction between NaOH and ethyl acetate in packed bed reactor. As you can see, we have collected all the readings of all the group in all the batches. So for the sample calculation, we have taken the readings of two groups. The readings of two groups to validate the experiment by finding the value of rate constant K theoretically and graphically. So let's have a quick look on the readings of group 1. So in the group 1 reading, we have measured the flow rate in LPH and the burette reading is taken in ml. So for 5 lph, the butyrate reading is 12.5 ml. For 7.5 lph, the butyrate reading is 12.2 ml. For the flow rate 10 lph, the butyrate reading is 10.6 ml. For 12.5 lph, the butyrate reading is 9.1 ml. For flow rate 15 lph, flow rate of 15 lph, the butyrate reading is 8.9 ml. For the calculation part, we have the pre-assumed data as the volume of reactor is 1.3 liter, the normality of NOH is 0.1 gram mole per liter, the volume of HCl is 20 ml, the normality of HCl is 0.1 gram per liter, and the initial concentration of A is 0.1 gram mole per liter. For 5 lph, we have calculated the initial moles of HCl by multiplying the volume of HCl with normality of HCl, which comes out as 0.002 gram mole. In a similar way, the moles of NaOH are calculated by multiplying the volume of NaOH with the normality of NaOH. The difference between the initial moles of HCl and the moles of NaOH gives the value of HCl reacted, which is 7.5 into 10 to the power minus 4 gram mole. From the moles of HCl reacted, the value of concentration of A is calculated, which is 0.0375 gram mole per liter. The conversion of A is calculated as shown here. The mean residence time is also calculated, which comes out to be 7.8 minutes. For the flow rate of 5 lph, the rate constant is calculated for 5 lph, which comes out to be 2.1367 liter per mole minute. For 7.5 lph, the initial value of moles of HCl is 0.002 gram mole, but the value of moles of HCl reacted is 7.8 into 10 to the power minus 4 gram mole, which is greater than the value for 5 lph. This is because as the flow rate is increased, the volume of NaOH required for titration decreases, that is, more HCl is reacted. For this value of HCl reacted, the concentration is calculated, which is 0.039 gram mole per liter. The conversion is calculated. The mean residence time is also calculated for 7.5 lph, which comes out to be 5.2 minutes. And from these values, the value of rate constant K is calculated, which is 3.0078 liter per mole minute. In a similar way, for 10 lph, the initial moles of HCl, the moles of NaOH, and the value of HCl reacted is calculated, which comes out to be 9.4 into 10 to the power minus 4 gram mole. For this value of HCl reacted, the concentration of A is calculated, which is 0.047 gram mole per liter. From this value of concentration of A, the conversion of A is calculated. The mean residence time for 10 lph is calculated, which comes out to be 3.9 minutes. Conversion of A, which is 0.445. For 15 lph, the mean residence time is calculated, which comes out to be 2.6 minutes. From all these values, the rate constant is calculated for 15 lph, which comes out to be 3.084 liter per mole minute. 12.5 lph, the initial value of HCl is 0.02 gram mole. The value of HCl reacted comes out to be 1.09 into 10 to the power minus 3 gram mole. For this value of HCl, the concentration of A is calculated, which comes out to be 0.0545 gram mole per liter. From this value of concentration of A, the conversion of A is calculated, and also the mean residence time for 12.5 lph is calculated, which is 3.12 minutes. And from this value, the rate constant is calculated, which comes out to be 2.676 liter per mole minute. In a similar way, for 15 lph, the initial value of HCl is same, which is 0.002 gram mole. The value of HCl reacted is calculated, which comes out to be 1.11 into 10 to the power minus 3 gram mole. For this value of HCl,
the concentration of A is calculated, which is 0.055 gram mole per liter. From this value of concentration of A, the conversion, which is the value of K theoretical. And as for the value of K graphical, the graph is plotted between 1 upon Ca minus 1 upon Ca naught and the mean residence time. From the graph, the slope is calculated, which comes out to be 3.2, which is the value of K graphical. As you can see, the value of K graphical and the value of K theoretical are almost same. For better understanding of calculation of packed bed reactor, the similar calculations are also performed for the observation table of another group. In this observation table, for flow rate of 5 lph, the burette reading is 14 ml. For 7.5 lph, the burette reading is 13.5 ml. For flow rate 10 lph, the burette reading is 13.2 ml. For flow rate of 12.5 lph, the burette reading is 12.9 ml. For flow rate of 15 lph, the burette reading is 12.6 ml. As you can see, the pre-assumed data for this calculation is same as the above. As you can see, also the initial value of HCl is also 0.002 gram per liter, but the value of HCl reactors comes out to be 1. The calculation is performed for 5 lph. In this case also the value of HCl initial is 0.002 gram mole. But the value of HCl reacted comes out to be 6 into 10 to the power minus 4 gram mole. For this value of HCl reacted, the concentration of A is calculated, which comes out to be 0.030 gram mole per liter. For this value of concentration, the conversion is calculated, which is 0.70. For the flow rate of 5 lph, the mean residence time is calculated, which is 7.8 minutes. From the above values, the K is calculated, which comes out to be 2.9914 liter per mole minute. Similarly, the calculations are also done for 7.5 lph, 10 lph, 12.5 lph and 15 lph, and all the above values are tabulated in table. As you can see, for different flow rates, the value of rate constant K are calculated. From this value of K, the K average is calculated, which comes out to be 4.866. The value of rate constant is also calculated graphically, for which the graph is plotted between 1 upon Ca minus 1 upon Ca naught and mean residence time. For the above observation table, the slope comes out to be 4.736, which is the value of K graphical. As you can see, the value of K graphical and the value of K calculated theoretically are almost same.
Earlier part of the video, we have seen theory, procedure, calculation, and found out rate constant K. Now we will see the disadvantages and advantages of the packed bed reactors for saponification reactions. Packed bed reactors can be suitable choice for saponification reaction, which typically involve the hydrolysis of esters in the presence of alkali to produce soap and grease oil. However, their effectiveness depends on the specific processing. Here we will discuss advantages. Efficient use of catalyst. The solid catalyst in packed bed reactor provides a large high conversion rates. In optimized condition, packed bed reactors can achieve high conversion efficiencies for saponification reactions as compared to plug flow reactor. The advantages. Now let's move on to the disadvantages. First one is pressure drop issues. The packed bed can create a significant pressure drop, requiring more energy to mount liquid reactant through the reactor. Second is distribution. Uneven distribution can occur, leading to insufficient utilization of a catalyst and incomplete saponification. Thermal hotspots. If heat dissipation is uneven, it can lead to localized overheating, which may degrade the product quality or affect the catalyst performance.
Maintenance and calibration of a packed bed reactor used for the saponification reaction between sodium hydroxide and ethyl acetate, involves specific steps to ensure accuracy and efficiency. Check for any physical damage to the reactor body or packing material. Ensure the flow meters, pressure gauge are functional. Inspect the inlet and outlet connections for leaks. Flush the reactor with deionized water to remove residual reactants or products. Use a mild cleaning agent for any solid buildup. Avoid abrasive cleaning tools that may damage the packing or reactor walls. Packing replacement. Inspect the packing material periodically for signs of fouling, clogging, or degradation. Replace damaged or contaminated packing material to maintain uniform flow distribution. Corrosion prevention. Regularly inspect for corrosion, especially if the reactor operates with caustic solutions like NaOH. Apply a protective coating or replace corroded parts. Lubrication. Lubricated valves or mechanical seals to ensure smooth operation. Drainage system. Ensure that the drainage system is not clogged and can handle effluent efficiently. Storage. When not in use, ensure the reactor is completely dried and stored in a dust-free environment. Industrial application of packed bed reactor. Packed bed reactors are widely used in various industrial applications due to their ability to provide efficient contact between reactants and the catalytic or active surface. Some key industrial applications include catalytic reactions. Packed bed reactors are commonly used in the petrochemical industry for the process like catalytic cracking, hydrocracking, and reforming. In these reactions, the packed bed contains a solid catalyst that promotes the conversion of hydrocarbons into more valuable products like gasoline, diesel, and jet fuel. Ammonia synthesis. In ammonia production, packed bed reactors are employed in the Haber-Bosch process where nitrogen and hydrogen gases are reacted over a catalyst to produce ammonia. The packed bed configuration ensures that the gases are efficiently contacted with the catalyst, enhancing the reaction rate. Hydrogenation. In the food and chemical industries, packed bed reactors are used for hydrogenation reactions, such as converting unsaturated fats into saturated fats, or hydrogenating organic compounds like oils and solvents. A catalyst like palladium or nickel is used to facilitate the reaction. Bioengineering. In the field of biotechnology, packed bed reactors are used in fermentation and other biological processes, where microorganisms are immobilized on the surface of the packing material. This setup allows for continuous production of products like antibiotics, biofuels, and enzymes.